Hello, this is Ed Pegg Jr., and welcome to my talk on knots and crossing numbers. And one thing I was just wondering is why the font changed on my title there. Martin Gardner ran a column called Mathematical Games for Scientific American for 25 years, and he collected those in a series of books, and they were very influential for young mathematicians like myself. So this series has been expanding on some of the things Gardner wrote about. Of course, we've got many different demonstrations on knots that you can look at demonstrations.wolfram.com. So I thought I'd start by showing some of the items that were in Gardner. For example, this page here in Unexpected Hanging, actually I was reading his columns first in Scientific American. This was my first look at the various sorts of knots, and I found that fascinating. Um, the square knot here is shown as a non-alternating knot. All the other knots here basically alternate between an overcrossing and an undercrossing. So one puzzle you might want to think about is taking a square knot and trying to find its alternating form. With 8 crossings, there are 3 knots that you cannot make into an alternating form, and I'll be showing those on the next page. Another item he showed was how Mobius strips could do odd things. For example, you could cut them in half and get a strip with 2 twists, or you could do like Escher did here and cut it in half, a strip with 3 twists, and you get a knot. Here are the 3 knots that cannot be made into a non-alternating form. And he also introduced a concept called invertibility. So basically you put arrows on a knot and you try to see if you can make the same knot where the arrow is pointing the same way. This knot over here is the unique knot that you cannot invert. All other knots, you can do a series of moves and get the arrows on the knot to point the other way. In the second book, he talked about disentanglement puzzles, and many of those involve knots. For example, there's this puzzle here where you have to get the string off a series of interconnected loops. And there's many different variations on this puzzle, and they're related to gray codes. Here's the gray code here. Basically, we're arranging all the excuse me. We're arranging all the numbers 1 to 63 so that their binary form only varies by 1 bit with each step. And this is a way of rearranging the numbers so that their binary part only changes slightly with each form. And this is used on satellites. They use gray codes on satellites that are pointing at stars to detect their dimness. This is one way they've detected exoplanets because they're able to measure the light very finely by using a gray code so that they know exactly how the light level is changing without any big shifts. Okay. And the number of steps needed for a disentanglement steadily increases as you add loops. So if you have a whole bunch of loops, it could take 10,000 steps. One other item related to knots he talked about was the Császár polyhedron. Here's a picture of one. It's a very strange polyhedron with a hole that has a maximal number of triangles. It has, I believe, 14 triangles, which is the maximal possible for a polyhedron with just 7 vertices. And it turns out that the arrangement of points for it makes a unique knot. The tubes here show the unique variation, which gives a knot. This tube here is not. You can see it best in this viewpoint here. And apologies for my voice; it seems to be going out right now. If you look at polyhedron data, this is our polyhedron. The vertex coordinates just happen to be in the form given in Conway-Gordon's paper. They say that all sets of 7 points in 3D will always define at least one knot. And there's one arrangement of points, which they give in their paper, which has a unique knot. And it turns out that the Császár polyhedron uses that arrangement of points. And here's a demonstration that shows the Császár polyhedron, which I'm probably mispronouncing. We can morph it in various ways. And if you go to this demonstration, you'll be able to play with this unusual object in many ways. It can be kind of difficult to figure out what's going on, but here you can see that it is a torus. There's a hole going through it. He further showed how this is our polyhedron. If you look at there's there's two sets of Fano planes involved with this polyhedron, and from those you can make what's called a room square, and that room square, which is named after Thomas Room, can be used to solve the Kirkman schoolgirl problem. 15 young ladies in a school walk 3 abreast for 7 days in succession as regard to arrange them daily so that no two shall walk twice abreast. It turns out that this room square, which you can get from the polyhedron, is similar to the one Cayley used in the same way years before Thomas Room was born in 1850, if I remember right. And basically, you arrange a set of 28 double-8 dominoes without blanks or doubles in this configuration. That's what Cayley did. And then for the first day, each number and letter corresponds to one of the 15 schoolgirls. So one group for the first day, it's ABC walk together, D35, E17, F28, and G46. Those are how. That's the first day for the problem, and then the next day is A to E, B26, C48, F15, G37, and so on. And that gives a solution to the problem all 7 days, where every one of the schoolgirls is next to one of the others at least once, and only once, for all 7 days. If we take the dual of the Császár polyhedron, we get the velocity polyhedron, which is shown here, and that's related to both the Fano plane and the Haywood graph. So a Fano plane has 7 points and 7 lines. If you show how they connect, you get the Haywood graph. And you can actually put the lines of the Fano plane on the vertices and the numbers. For example, 6 is connected to 167, 167 connects to 1, 6, and 7. We can also draw the Haywood graph with only 3 crossings. Here's 2 ways of doing it. Here the graph is drawn with only 3 crossings, and here the graph is only has 3 crossings. Figuring out what the fewest number of crossings is for a given graph, it gets difficult, especially as the graph gets large. Here's another graph that I played around with quite a bit, is the utility problem. You have electricity, gas, and water need to connect the 3 houses, and you don't want any of the lines to cross. It turns out it's impossible to do that unless you cheat in some way by putting a pipe under a house or something like that. But without cheating, it's impossible for the lines not to cross, which I didn't believe. I tried this hundreds of times and of course never succeeded. So the simplest way to present a graph is, if it's planar, is just to draw the planar graph. The tut embedding works very well for that. For non-planar graphs, it can be a lot trickier. Here's many different representations for the Peterson graph, and 2 of them are shown in a 2 crossing form. This one and this one both have 2 crossings. The problem became famous after World War II. Paul Turan was basically sent to a work camp, which was a euphemism for they were trying to kill him and everybody else who worked at the camp. But they also needed these bricks, so it wasn't too onerous. They worked at a brick factory. They pushed loads of bricks around, and the carts were on tracks which had to cross each other. And every time there was a crossing, there was a danger that the bricks would spill out and the prisoner would get punished, and that would slow things down. So he tried to come up with a way of minimizing the number of crossings for tracks. And he actually wrote up a paper for this while at the prison work camp, managed to smuggle that out of the camp to some people that could publish it, and he was publishing papers while he was being worked to death. And then he gave a number of talks about this problem and other related problems after the war was over. So one thing I noticed was that the Peterson graph and the Haywood graph, you could basically add an edge to the Peterson graph and get the Haywood graph. And I wondered if there was a group of related graphs where they were minimal. There were the smallest graphs that required a given number of crossings. So I worked with Geoff Exu on this, and we came up with what we called crossing number graphs. So the utility graph is the smallest one. It requires, it's 6 points that requires a crossing. And these are all cubic graphs. Each vertex connects to 3 edges. So these are all cubic graphs. And with 10 vertices, you can require 2 crossings, and there's 2 ways of doing it. Here's the other graph. For 14 vertices, there's 8 different ways of drawing a graph that require 3 crossings. One of them being the Haywood graph, the other being the generalized Peterson graph, and there's also these others here, less well known. Moving up to 16 vertices, there are 2 different graphs that require that force 4 crossings. One of them is the famous Mobius-Cantor graph, which you can get by adding 1 edge to the Haywood graph. Moving up again, the next graph in the chain with 16 vertices is the Pappus graph, which you can get from the Mobius-Cantor graph by adding 1 edge between 2 edges. And again, you can get the smallest graph that requires 6 crossings, the Sarg's graph, by adding 1 edge to the Pappus graph. And there's different variations for each of these. And we thought that there would be another famous graph requiring 7 crossings if we just added 1 edge to the Sarg's graph. Well, it turns out that wasn't the case. You can add an edge and require 7 crossings, but none of these 4 graphs with requiring 7 crossings is all that famous. But if you add an edge to to those, you get two famous graphs that require 8 crossings, the McGee graph and the Nauru graph. And then 3 steps up, you get the Kochler graph. And after that, 2 steps up, you get the Levy graph. So these are all heavily interconnected graphs. By adding and removing edges, you get the minimal crossing number graphs. So that's graphs. You can also try to figure out crossings for knots. And knot data has knot data for knots of up to 10 crossings. There's a unique 3 crossing knot, a unique 1 crossing knot, 2 5 crossing knots, and so on. So here's a few of the properties that you can look at for knots, and I'll be going over many of these. So first, may as well look at some pictures of knots. Here's the overhand or trefoil knot and the figure 8 knot. And that's usually where people stop as far as knowledge about knots. This one is the Solomon seal knot and the stevedores knot here. And most of these others, in terms of mathematical terms, don't have names. Sort of knots that are useful for climbing or horse riding or fishing or backpacking or sailing. Usually those knots depend more on friction than on the shape of the knot. So things like the cleat hitch or the trucker's hitch or half hitches or uni knots, most of those aren't as mathematical as the way they're defined here, because they're usually not closed loops. Usually there's 2 ends and there's a lot of friction involved with how the knot is made. Sometimes there is a release on them so that they can quickly be untied. So these are various small knots. There's a braid diagram. If the braids are wrapped around a cylinder, that's one way of representing the knot with a minimal number of braids. There's also a 3D version, which isn't 3D here because it was taking too much. Oh, did I just delete it? Let's see if we can reverse that. And it looks like it's gone. And a knot diagram. So one thing I've never quite understood is how to make knot polynomials. So I finally, for this talk, figured out how it all works. So we take a knot, such as the figure 8 knot here, and we label all of the intersection points, 1, 2, 3, and 4, and we label all the regions defined by the knot, 1, 2, 3, 4, 5, and 6. And then for a given intersection, for example, intersection 1 over here in this version over here, we arrange it. Oh, no, I forgot to mention. And we also put a directional arrow on the knot so that it's oriented. So for this version over here, here's intersection number 1. And the next step, which is the part I'd never quite understood, is we arrange the arrows so that they both go up for that intersection. So here, these arrows are going up and these arrows are going up. And then we find which one of these 2 diagrams it matches with. And it matches this diagram. The arrow is going this way over that one. And that's what's going on here. In various books and papers, it has a very complicated description of how to do that I never understood. But with these pictures, I was able to figure out. So then for vertex number 1 here, 1 corresponds to T. So we can put a T here. 2 is not connected to 1, so it gets a 0. So we put a 0 here. 3 corresponds to -1. We put a -1 here. And 4 is at the bottom here, corresponds to -t, so we put a -t here. And then we can do 1, 2, 3, and 4 for the under and over crossings. The next step was, once you build up the whole incidence matrix between intersections and regions, you can delete 2 connected regions. So you could delete regions 5 and 6, those 2 columns of the knot. And then we take the transpose and the determinant. And it turns out you get this equation here, which is the Alexander polynomial for the knot. Oops, switching it. Oh, this was the figure 8 knot. It's this one here. 3 minus 1 over x minus x, 3 minus 1 over t minus t. So this method does work, but it really helps to have these diagrams if you're not well versed in how building these incidence matrices works. So there's very many different types of polynomials. The Alexander polynomial was the first one that was found, and then several other polynomials were found after that. The Conway polynomial is sort of a simplification of the Alexander polynomial that takes a 1 over x and x and basically replaces it with x squared. So that gives a simpler form for the polynomials. The other ones, such as like the BLM-Hode and the bracket polynomial and the Jones polynomial, are a bit more complicated, as you can see, for these various knots. And then much more complicated are the Holmfly and Kaufman polynomials of a knot. I did not bother learning how those work exactly. We have a demonstration that can do an interactive form for these. For example, this knot here, I think we can add a vertex. So let's add a vertex here. Oops. Let's move this out of the way. Let's move this way out of the way. That's not letting me add another vertex. So we can put these back together here, switch that to an overcrossing, and let's switch these as well. Let's put that one back. And what else? Let's see what this knot is. So this is the 4-1 knot here. So this is an interactive Alexander polynomial. We can take a look at all the various Conway polynomials for the knots, and that kind of gives an understanding for the knot structure if you understand how the polynomial works, which I don't, but apparently this one and this one are somewhat simpler for the knots, and 7-1 is a more complicated one. One item that I do understand well is Gauss codes. So basically, just draw any closed loop on a piece of paper and eventually get back to where you started. And try to keep the intersections away from each other. And then start anywhere. I'll pick this intersection here. And then start following the loop. Label the first intersection 1. And then skip one intersection. Label the next intersection 2. Skip an intersection, label the next one 3. Skip one, label the next one 4, and so on. And if you keep going around and label the intersections, adding numbers to every other intersection, eventually you'll label all of the intersections without overlap. And this is something that Gauss noticed. And for this set, we end with 17 here. So there's basically two parts of this. You get the regular set of intersections, which is the ones we numbered, 1 to 17. And then if you take the numbers in between, the number in between 1 and 2, the number in between 2 and 3, and so forth, you get a permutation of 1 to 17. And that's the Gauss code for the loop that you drew. So if this was an alternating knot, this would be a unique representation, but not all knots are alternating, so you can't get all knots with Gauss codes. And I wrote a demonstration where basically you could take one of these and you basically make a path based on the Gauss code. So for example, this diagram here is a diagram for this particular permutation. Now, one thing I haven't figured out is how to come up with a good closed loop which is faithful to the overcrossing, undercrossing. There's probably a problem here with, for example, I'm going 1 to 5 to 2, but this is not a crossing here. There should be a crossing from 1, 5 to 2 that goes over the path. And I'm not sure how to make this so that it's actually over and under crossings. They just kind of touch each other at that location. And this is just one I picked randomly. Most of these graphs that are constructed with this technique have that problem. I'm not sure how to fix it. So I found that there are a given number of distinct graphs that come out of these permutations, but many of these graphs have problems and I'm not sure how to correctly count them or fix them. So one question I haven't been able to solve is how many distinct Gauss codes are there for closed loops? And that's a problem I'd like to hear the answer for. It may have been solved already. In fact, Gauss may have solved it, but it's something I haven't been able to find the answer for. One thing I mentioned for Conway is that 7 points, if they're in the standard position, and that means there's no 4 points on a plane, and also no 3 points on a line. If 3 points are in the standard position, then at least one of the 7 cycles is knotted. So here's some examples of 7 points in the standard position, and these are minimal integer coordinates. There's I think for this small region, there's exactly 23 ways of arranging 7 points so that no 4 are on a plane. For each of these sets, there's at least one 7 cycle that is knotted, but there's 360 ways of finding a loop, and often only 1 or 2 of them will be knotted, and finding that particular knotted one is tricky. I'm not sure how to automate that either, but it's something that's something I'd like to do. We can take a look at these braid diagrams. The number of braids in it, for example, this one has 3 braids, so its braid index is 3. This one here has 5 braids, so its braid index is 5. And the smallest braid index you can have is 2, for example, these 2. We can look at true false values for knots. Let me make this smaller here. Here we go. A lot of our properties, such as alternating, hyperbolic, invertible, satellite, and torus, there's also a reverse form that is given. So if it's true for one, it's false for the other. So these are some of the properties that we can have for knots. I've already mentioned whether a knot is invertible, if you can change the orientation, or if it's alternating, if you can arrange the knot so that the crossings alternate over and under. One thing I don't know is whether there's a knot with a minimal crossing and it has a alternating form if you go for more crossings. I'm not sure what property that would be. And there's also a lot of numbers involved with knots. And that's one of the reasons I made this particular talk, because the unknotting number was something that was just solved last week. This paper here, the unknotting number is not additive. So basically what they found in this paper last week was that if you took two copies of this knot and joined this and its mirror image together, say at this point, just imagine mirroring this knot and connecting them here, the unknotting number for that combined knot is just 5, whereas the unknotting number for that knot is 3. If the unknotting number was additive for a connected sum, then the unknotting number would be 6 instead. And after noticing that, they were able to come up with an infinite whole series of examples where the unknotting number was not additive. And that paper just came out a few days ago. So here are various numbers related to graphs that we have in knot data. One other thing you can often do with knots is minimize the number of bridges. A bridge is a segment that has one or more overcrossings. So here are two representations for the overhand knot, which each have 2 bridges. It's not easy to see, though, that these are both the overhand knot. Here's the figure 8 knot, which is a little bit more complicated to do in a 2-bridge form. And this is a new resource function, a 2-bridge knot diagram. So here are knots 6-1, 6-2, and 6-3 in the 2-bridge form. They can get more and more involved. But most knots require more bridges. Out of 1.7 million knots with up to 16 crossings, only about 5.5 thousand are 2-bridge knots. So one thing I'd like to do is come up with a way of making 3-bridge diagrams, but those are rather complicated. I haven't figured out how to do that yet. There are other knot properties. The Conway string is one way of encoding the sequence of tangles in a knot, and the Dowker notation is similar. So here are various presentations for the simplest knots here. And I'm hoping to figure out how the Docker notation and Conway notations work, but I wasn't able to figure out exactly how they work in a way that I could explain them within a few minutes. So I'm still working on understanding some of these. Usually I don't consider that I understand something until I can use a picture to explain it in less than a minute. And I'm just not there yet. Of course, these are very difficult concepts, so I'm not sure whether it's possible to explain these in an easy way. In other news, there's other things that have been happening. My friend George Seekerman figured out how to place pentominoes in a grid so that there's exactly 5 squares in every row and column. So sort of a Sudoku problem for pentominoes, and no 2 polyominoes touch each other except at corners. So this was actually a long-standing problem, whether it's possible to do this, and George Seekerman solved it last week. One other thing we had Yesterday, or was it the day before yesterday? Day before yesterday was 9/16/25 or 16/9/25. And it turns out that the Pythagoras figure that comes out of the 3, 4, 5 triangle can be divided into 56 identical triangles. In fact, the 1, 2, square root of 5 triangle. And this is one way of doing it, this diagram here. One thing coming up, I think next Saturday, let's see, that would be what, 9/27/2025, if I remember this right. I think that's a square number, yes. So if you like in month day format, 9/27/2025, you can get a square number. What happens if we do it the other way? Let's see. 27/09/2025. So here's the day, month, year format. Oh, and it's also a square number. So in either way, if you do month day format or day month format for September 27th or 27th of September, you get a square number. Which is something I show here. One other thing that recently came out, this is what's called the Rupert's cube problem, Prince Rupert. Canada used to be called a Rupert land. So, and one of the problems he showed was that you could take a cube and pass a larger cube through it if you drilled a hole through it. And this is known as Prince Rupert's cube. He named a whole bunch of things after himself. One of the things you can do is if you drop molten glass into water, you get these tadpole-like structures where you have a very hard bulb at one side and a fragile tail at the other. And if you break the tail, the whole thing shatters. But the bulb is extremely hard. You can hammer it and it won't break. And that's a Rupert's glass, I think it's called. So one open question was whether all polyhedra had the Rupert property, that you could drill a hole through it and pass the polyhedra through itself. Well, it turns out that no, this object here, which is now called the Noperthedron, which was found just a few weeks ago, does not have the Rupert property, so it's called the Noperthedron. And here's how to make one here. And at the same time that was announced, the Hudson Bay Company folded. It got liquidated. Just this month, the oldest running company in North America, until last month, it finally ended and was liquidated at about the same time that this object was found. So the company that Prince Rupert founded, the Hudson Bay Company, is now gone, and his famous problem that he was related with is now solved. I thought that was an interesting juxtaposition for something that's been going on since 1670. There's other resources you can do for knots. This link here, and this paper will be at Community sometime soon. This whole talk will be there along with all these various links. This link here has a lot of data on crossing numbers. Knot info has a lot of lookup tables for knots, and the knot atlas has a whole bunch of pictures and other information about knots, some of which I used in this talk. And of course, there's many unsolved problems with knots. For example, if we go beyond a crossing number of 14, there's very little I know about cubic graphs. So what the next graphs are in the crossing number graphs is something I haven't figured out. And even something as simple as what are the quartic crossing number graphs? That's a problem that probably anyone could solve, but it's something we haven't collected data on yet. So that's what I had, and I'll be glad to answer any questions if anybody has them. Stephen Wolfram will soon be giving a talk as well, so I don't want to overstep his talk. I'm not sure where that talk will be located, but perhaps somebody can post a link into the chat if they know. But that's what I had prepared, and I'll be glad to answer any questions. Oh, all right. Many thanks. And thanks for attending my talk.